G'day everyone. Today we're going to be learning about series and finance. In this lesson specifically, it's going to be focused on investing money in installments. Today we'll be taking a look at how geometric series apply in this sort of context and the basic building blocks that we need to understand in order to answer certain questions, as well as taking a look at a few examples and applying this information. So let's get into it. So this blurb here gives a general guide on how to answer these sorts of questions. So before I get into what these dot points are saying, I'm going to give you context into what these questions might be. So generally, the question will contain a regular deposit. Let's call it amount D for deposit. And we invest, or we put this deposit in the bank for, let's say, 10 years. And at every year, we make the same deposit. So this will be our year. And at year 1, we put in our deposit. In year 2, we put in another deposit. Year 3, we put in another deposit. And we keep going until the 10th year where we make a deposit. All of these deposits are accumulating interest in our bank account. Let's say the interest is 10%. Per annum. So that means per year, we're going to be earning 10% interest. Now, using our compound interest formula, what we'll be able to see is that based off this deposit, after 10 years, the compound interest or the amount that we will have in the bank account from this deposit will be D times 1 plus our rate, which is 10%, to the power of 10 years. On the second year, we still have this 10% per annum rate. However, it's being accumulated interest for only 9 years. So we have something like this. And for our third year, what we'll be able to see is it's the exact same formula, except the power is to the 8. And then on our last deposit, sorry, I just noticed this error here. I'll rub this out. On our last deposit, it will only be accumulating interest for 1 year. And essentially, when we add all of these terms together, what we'll get is our final value, or at least the value that will be showing in our bank account at the end of these 10 years after all of the deposits that we've made have accumulated interest. So this is essentially the building block of what the questions are going to be based around. And so if we look at the blurb here, these 2 dot points, the first statement says, find what each installment will amount to as it earns compound interest. And that's what we've sort of done here. So each installment is each deposit, and we've calculated the amount that it earns as it accumulates compound interest. And the second dot point says, add up all these amounts using the formula for the sum of a GP. So how do we go about adding up all of these future value deposits together? Well, what we need to realize is that we can form a GP to answer this question and essentially use the equation for a sum of a GP, and that will get us our answer. So to re-jog our memory, the formula of the sum of the first n terms of a geometric series is a outside of r to the n minus 1 over r minus 1. So this is a key formula that we are going to be using to answer these sorts of questions. And so now let's take a look at 2 examples in applying this information. The first example says each year on her birthday, Jane's parents put $20 into an investment account, earning 9.5% per annum compound interest. The first deposit took place on the day of her birth, and on her 18th birthday, Jane's parents gave her the account and $20 cash in hand. Part A says how much money had Jane's parents deposited in the account. So before we get into that question, let's break down the situation. What we have is Jane and her parents are depositing $20 into her account every year, starting the day she was born. So let's take it as her age. And so when her age and the deposit amount. So when her age is 0, or on the day of her birth, they deposit 20. When her age is 1, when she turns 1, they deposit 20. When she's 2, they also deposit 20. And this continues until she's 17, where they deposit 20. And on her 18th birthday, they actually don't deposit anything. Instead, they give her just $20 cash in hand. Think of it this way: they could deposit the $20, but they are immediately withdrawing the money on her 18th birthday. So that $20 would just be going in the bank account and straight out. So that's why they've sort of specified this here to say it's $20 cash in hand. So now we can get into part A, which is how much money had Jane's parents deposited in the account. And so that amount is, well, specifically in the bank account, it's going to be the amount they deposited for those first 17 years. And so, or 18 years actually, because we're including when she was born at age 0. And so what we have is 18 installments, or 18 deposits of $20 that they make, and we multiply that by 20. And what this equals is $360. So these are the installments from age 0 up until age 17. Remember, we aren't including this age 18 installment here because this is represented by $20 cash in hand, and it is not in the account as the question specifies. Part B then says, how much money did she receive from her parents on her 18th birthday? So this question now requires us to use the future value or the compound interest formula to work out how much money she eventually receives on her 18th birthday. So what we can do here is we can set it up so that the future value at age 0 is equal to the $20 deposit compounded 9.5% per annum. So that's 1 plus 9.5%, and it's raised to the power of 18 because it is sitting in the bank account for 18 years. You might say, well, why not 17 years? Well, the reason being is because at age 0 to age 1, this is 1 year, and then this will be another year, and so on. And so by the time you reach the 18th year, you'll accumulate 18 years worth of interest. So that's why we have 18 there. The future value at from the first deposit at age 1 is 20 outside of 1 plus 9.5% to the power of 17, because that's getting accumulated for 17 years. The future value of the second year deposit is 20 outside 1 plus 9.5% to the power of 16. And this continues until the future value of age 18, which is just the $20 cash in hand that the parents give her. So now, when we try and put this all together, remember the first dot point that we encountered was to work out what the accumulated compound interest is going to be for each installment. And now the second part of the process is to sum these all together by using a GP. So when we look at the sum, or the total future value, we can write this as, it's better to write this as an increasing formula. I think it makes it easier. So let's start from the end and work our way up. So what we get is 20 plus 20 outside of 1 plus 9.5% to the power of 1 plus 20, 1 plus 9.5% to the power of 2. And this will continue all the way up to 20 outside of 1 plus 9.5% to the power of 18. And so from here, what we can realize is that this is GP with our A, our first term, as 20, and our ratio as 1 plus 9.5%, or 1.095. And so what we can then say is that we're using the sum of a GP, which is Sn equals a outside of r to the n minus 1 over r minus 1. When we plug in these formulas, we get that the future value is equal to 20 outside of 1.095 to the power of 19. So our n is 19 because there are 19 terms within this series. This is minus 1 over 1.095 minus 1. And when we plug this into a calculator, what we end up getting is $970.27. And that's our final answer. Another question that they might ask is how much interest did Jane earn on this deposit? And interest is essentially the amount accumulated on top of what you've deposited. So the interest for this question would just be the $970.27 that was accumulated, or that was the final value at the end of all of these 18 years, minus the $360 that the parents directly deposited. And so when we subtract these two, what we end up getting is $610.27 in interest. This is just a side question that you may encounter, and it wasn't directly asked in this example, but I thought it would be a useful exercise to go through. So I hope that question made sense. Let's take a look at another example. This next example says a couple saves $100 at the start of each week in an account paying 10.4% per annum interest, compounded weekly. Let AN be the amount in the account at the end of the nth week. So what we have here is a situation where they deposit $100 at the start of each week, and it pays 10.4% per annum interest compounded weekly. So our interest rate is 10.4% per annum, but because it's compounded weekly, we want to work this out as a weekly rate. So if we take 10.4% and divide it by the number of weeks in the year, what we get is 0.2% per week. And that is going to be our compounding rate that we're going to be using for all these parts here. So then they're saying let AN be the amount in the account at the end of the nth week. So part A says explain why A1 equals 1.002 times 100 and why AN plus 1 equals 1.002 times 100 plus AN. So what we can say is that A1 equals 1.002 times 100 because it is the amount at the end of the nth week, and A1 would be the amount at the end of the first week. So it is the $100 deposit that they make times 1 plus 0.2% per week interest to the power of 1 week. And so this essentially just equates to 1.002, which is just this, multiplied by 100. Now, they also want us to explain why AN plus 1 equals 1.002 times 100 plus AN. So what this is saying is that, well, when we have AN, this is the amount in the account after n weeks. So amount after n weeks. And essentially what happens after the nth week is that when we want to consider the n plus 1th week, so the week after AN, we take the amount that we already have, we deposit $100 into it, and this accumulates 1 plus 0.2% per week interest for 1 week. And so that just means it's 1.002 times 100 plus a to the n. And that's, I guess, how this series, or how this formula actually works. And this is sort of how we would explain part A. Part B then says use these recursive formulae to obtain expressions for A2, A3, all the way until AN. So what we can say then is that, well, A2 is equal to the A1 plus 100 times 1.002, which is equal to, what is it equal to? It's equal to 1.002 times 100 plus 100 times 1.002. And so all I've done here is taken this value for A1 and substituted it into here. Now, when we sort of expand this formula, what we can see is that the 1.002 gets multiplied in both these terms. And what we end up getting is 1.002 squared times 100 plus 100 times 1.002. I'm just going to rewrite this and say it's 1.002 times 100 plus 1.002 squared times 100. A3 then becomes 1.002 outside of A2 plus 100, which is equal to 1.002 outside of, now A2, I'm just going to repeat what we have here, which is 1.002 times 100 plus 1.002 squared times 100. And then this is just getting added to a 100. And when we simplify this, what we end up getting is 1.002 times 100, which is what you get when you multiply these together. And then when you multiply by that and that together, what you then get is 1.002 squared times 100 plus 1.002 cubed times 100. And we can continue this pattern and go on and on and on, but hopefully what you can realize is that AN, which is the amount in the account at the end of n weeks, is 1.002 times 100 plus 1.002 squared times 100. And this will keep going until we get 1.002 to the power of n. So whatever our n is going to be, that's sort of the term that we stop at, times 100. And that is essentially our answer for part B. Part C then says, using GP formulae, show that AN equals all of this. So using GP formulae show that AN equals that expression they showed up above. So what we realize is that this is a GP, and what we can say is that our A, actually what I'm going to do is I'm going to factor this to make it a bit simpler. What I can say is I can factor a 100 out of our AN. So I can say it's 100 outside of 1.002 plus 1.002 squared plus all the way up to 1.002 to the power of n. And so now this section here is a GP, and it's a GP with A equals 1.002. Our R is equal to 1.002, and our n, the number of terms, is equal to n. So when we want to simplify this expression now, recalling that the sum of n terms of a GP is A outside of R to the n minus 1 over R minus 1, we can say that this is 100 times the sum of this GP, which is, well, following the formula, it's going to be 1.002 outside of 1.002 to the n minus 1 over 1.002 minus 1. We need to prove that it's equal to this expression here. And what I want you to notice is that, see this 1.002 minus 2 to the n minus 1, this is equivalent to what we have over here. And then the only other thing that we have within this expression is this 50,100, which should indicate to us that, well, everything else that's outside of the 1.002n minus 1, everything else should equal 50,100. So this whole bit here, it should equal that. And so when we put this in the calculator, I'm going to make this a lot clearer. Specifically, when we put this in the calculator, let's work out what we get. And yep, you could guess it. We get 50,100 outside of 1.002 to the n minus 1. And that is how we would go about solving part C. Now part D, if we scroll up, says hence find how many weeks it will be before the couple has $100,000. So how many weeks will it be before the couple has $100,000? This is just saying after how many weeks, n weeks, will the amount AN be greater than or equal to $100,000. And so it's very simple. Considering we have AN already, and we have this simple formula for AN. And so we solve for the equation where 50,100 outside of 1.002 to the n minus 1 is greater than or equal to 100,000. Now, when we divide by 50,100 on both sides, what we get is 1.002 to the n minus 1 is greater than or equal to 1.996, so on. When we add 1 to both sides, we get 2.996, and so on. And what we can do is log both sides. And the purpose of logging both sides is for us to bring this power down. So we can say this is now n times ln 1.002 greater than or equal to ln 2.996. And then to figure out n, so we say n is greater than or equal to ln 2.996 over ln 1.002. Plugging this into a calculator, we get n is greater than or equal to 549.188, so on. Now this is weeks. And so the first week in which they will hit at least $100,000 is 550,000, because that is the first whole number for n that is greater than this number here. It's not going to be 549 because if it's 549, they won't have more than $100,000 just yet. It only happens in that 550th week. So therefore, after n equals 550 weeks. Now, if we wanted to translate that into years, we would divide this by 52 and realize that it's 10.58 years. But that's the general gist of how we would go about doing this question, and this is the answer that we get. So I hope in this lesson you were able to learn a few things. To recap, we just covered the general process of how you can apply sequences and series or geometric series in finance, specifically finding the future value of monthly installments that are compounded. Please leave a comment if you have any questions about any of the content that we've covered here today. Please leave a like and subscribe if you found it useful, and stay tuned for more videos. Thank you.